Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 78. So in the previous lecture, that is lecture number 77, we were discussing about how meteorites were postulated to be very actively involved in the formation of Earth itself. There of course are experimental evidence, and we saw that there are two prominent theories, one being the cold accretion theory. As part of it, the rocky substances which were initially formed from the solar nebula, they got separated out in cold conditions, and they kept accruing, and they come together. They grew in mass sufficiently enough, in size, okay, because they contain nuclear active substance such as like 238 uranium, 27 aluminum, etc., etc. And because of this cold rocky mass, it gets heated, and it can get heated even to temperature as high as 1500 Kelvin. And as the temperature reaches approximately 1500 Kelvin, what happens is that, highly dense material, such as, for example, iron and iron sulfur systems, okay, I mean minerals containing iron, sulfur, etc., they get molten, they get melted. Right? So they get melted, and what happens is they sink to form what is called as a core, and sink to form a core. It's a very dense core, form a dense core. Now, as this core is getting formed, all other lighter substances, I would say I have to quantify it, okay. Almost all other substances, barring, some highly dense material. So it's almost all, okay, right? Gases, solids, and liquids. Note that initially we're talking about an active solid mass, but due to the rise in temperature, different things get melted. Some of them become, they go to the gaseous phase, some of them go to the liquid phase, etc., etc. They all get sputtered around, resulting in an atmosphere of gases, because the gases are the lightest, right? So they stay on top, resulting in an atmosphere of gases. And the surface containing with some solids and liquids. So what I've written here is, so as the temperature suddenly rises and the densest stuff gets melted and it forms the core, all other substance, that they just get sputtered around this, and the lightest gases form the atmospheric layer. In fact, we're looking into a very important event, which is the formation of the atmosphere. There are very stringent timelines associated with these processes, but the more details of which can be studied from an astrogeology course, okay, right? But for our purpose, it's sufficient if we understand broadly as to how the atmosphere was created and how the other liquids and solids, would form the part of the surface, and in some depth, with the deepest parts, that is the core, being occupied by a very dense material. So this is the cold accretion theory, wherein the rocky substances or the meteorites started out as being very cold, but due to nuclear activity, right? As part nuclear activity from the material as part of the rocky substance, the rocks got heated eventually, and that resulted in the structure of Earth as we know today. Okay, so this is the cold accretion theory. Now, as part of the hot accretion theory, which is a competitive to this theory, of course, this theory has various evidence based on, you know, the rate at which iron gets melted and the radiometric dating, such as, like, looking at the nuclear activity, etc., etc. But recall that all of these are, we of course have experimental data, but we have to tie them with hypotheses. So while this is one plausible hypothesis, one can never say for certain that this is the way in which Earth was formed. Okay, so I'll now go on to the other famous theory, which is the hot accretion theory. Now, as part of this hot accretion theory, of course, you know, as the rocky substances eventually from the meteorites separated out, they were partially melted. Now, this has been found, okay, this even very close to the sun itself, some meteorites have been known to be already partially melted. All right, so therefore, they were already hot. So the point is, it's not that, you know, like the rocky mass that eventually became Earth was cold to begin with, and then due to nuclear activity got heated. It was that they were already very hot to begin with. Okay, and because they were already hot, and what is the evidence for it? The evidence for it is meteorites close enough. I'm not quantifying how much. Close enough to sun are noted to be partly in the molten state. So this is an experimental measure, but I'm not telling you what experiments were performed and how exactly this was obtained. Okay, I mean, due to a want of time, but notice that this is the crux of the story. So based on this evidence, the meteorites were already hot, and so, you know, when they all accrue together, when enough mass is reached, when enough mass is accrued, what happens is that the heat, okay, right, the heat energy that is present in the meteorites, the heat in meteorites cause volcanic eruptions. Okay, right? So, you know, there's a lot of turbulence. We're talking about a very hot system, and that results in temperatures as high as 1500 Kelvin. All right. And what happens next? Of course, you know, as the temperature becomes very high, as we discussed in the cold accretion theory, then the iron sulfide, etc., they get melted, and so they form a dense core, and all other light substance, right, including the water and then several solids found on the surface or closer to the surface of Earth, they stay there, and the lightest gases, they form the atmosphere of the Earth. All right. So these are the two theories, the cold accretion theory and the hot accretion theory, which are extremely critical in understanding how the Earth was formed. These are the top two contenders, and evidence, you know, for each of these, like, keeps coming back and forth. We don't know the final verdict, but these are interesting hypotheses. Are we good? Okay. So, in short, so far we have been looking into the chemistry of meteorites. I mean, of course, there is a lot more to discuss, but due to want of time, I shall now take you to the next topic, which is the chemistry of the comets. Oh, by the way, before I go to the chemistry of comets, notice that in the solar system, this is just a general knowledge fact, a lot of the meteorite belts are found, a lot of the meteorites currently, okay, they have their origin between Mars and Jupiter. And some between Jupiter and Saturn also, but predominantly between Mars and Jupiter, you have a huge belt, which results in a lot of these meteorites. So next, we move on to the topic of comets and the chemistry of comets. Okay, I think once again, if you go back to lectures 4 or 5, the origin of comets has been discussed. Okay, how are broadly comets formed? Well, comets are roughly going to be composed of ices as opposed to the rocks which constitute meteorites. Okay, so these ices is predominantly made of a volatile inventory of organic and some inorganic molecules also. So that is the composition of comets, which we have kind of looked into, and we don't need to go into details right now. But what is important is a lot of these comets, okay, they originate, a lot of comets known in the solar system, a lot of comets in our solar system originate in two dominant belts, okay, right? In two regions close to Neptune and Pluto. So, I mean, these are the planets, right? I mean, Neptune and Pluto is considered a planet by some and a dwarf planet by others. Okay, I'll come back to that soon. So, this is where they originate, and I think they're dominantly named as Kuiper Belt and the Oort Belt. And again, I'm not quantifying how close. We're talking about a few thousands of light years also. Okay, right? That's what is meant by close in this context. I'm intentionally not quantifying it because that is something that you could look up as a detail when you especially pursue it as an area of research. For an introductory idea of, the understanding of chemistry of comets, this is sufficient. All right. So a lot of these comets, they originate from there and move towards the sun from very far apart. Okay, and generally move towards the sun. While they move, they have a fascinating structure. Okay, the comet has a fascinating structure, and I'll be talking about it next. So the structure of a comet. So the comet, contains of a dense nucleus with some surrounding materials and comprises of generally, two visible tails. This is some tail 1 and this is a tail 2. So this is the dense nucleus, which is roughly, of the order of, let's say a dozen kilometers or so, approximately 10 kilometers. There is an envelope, of like molecules. The nucleus is also comprised of molecules. The dense region, the area surrounding it is also comprising of molecules. And this is the diameter of this region is of the order of 10 to the power 5 kilometers. And you have two distinct tails. Okay, right? The one tail comprises of, so this is, let's call this tail 1. And this comprises of a lot of neutral molecules. So you have another tail which comprises of a lot of charged ions. This is superb. The neutral molecules are part of one tail, and the charged ions are part of another tail. So these are. See. So what happens is, as this highly volatile bunch of molecules or volatile ice, they come towards the sun due to a thermal gradient. Okay, because further away from the sun, the temperature is colder, and as we move towards the sun, the temperature gets hotter and hotter, right? So due to a thermal gradient, there's a constant loss of material from the center, the dense thing, and that was what results in this tail. Okay, right? So the neutral molecules, the tail of neutral molecules, T1 is formed majorly due to a thermal gradient. But what about the charged ions? Why should charged ions be formed in the first place, right? This is fascinating. Now, this is arising due to the magnetic field of the solar system, especially, of the sun. So this is due to the magnetic field. In fact, without going into the math, very intuitively and qualitatively, almost like a layperson, you can see, why magnetic field could align all the ions in one direction. Because typically, a lot of paramagnetic and ferromagnetic substances, they are ions, right? A lot of metals and metal ions on Earth. So it is easy to see that the magnetic field could align all the metals. So this metals and metal ions, okay? So this combination of ions is what is typically referred to as a plasma. That is, see, you must have heard about the word plasma, but for our purpose, this this assorted presence of ions in one region is what is called a collection. Yeah, I was looking for the word. Okay, the collection of ions is what is called as plasma. So this is the tail comprising of ions which arises due to the magnetic field, and this is a tail which arises due to the thermal gradient. So and so a comet, right? A comet originates typically from the outer regions of the solar system, and they keep moving towards the sun. All right. So what is the origin of the comet? Well, the origin is a bunch of volatile molecules weakly bound together in the form of ices. We discussed this in lecture 5 itself. Okay. And as they move towards, right, the end of a comet, or, you can call it very in a tongue-in-cheek way, the death of a comet happens typically as the material from the comet eventually gets exhausted, because see, these are volatile stuff. A lot of gases, the gas trail is left behind, right? As the material from the dense core is eventually exhausted. Well, how does it get exhausted? In some cases, it transfers some materials to the Earth's atmosphere, and of course to the atmosphere of several planets, their satellites, etc. And in that sense, the comet has a very important role. See, as far as meteorites are concerned, the samples fall on Earth, boom, right? But as far as comets are concerned, they, as they pass by Earth, right, they constantly, are a source of molecules for the Earth's atmosphere. Okay, so noted. As comets die, they deposit. Deposit is not the right word. Let's say, that some molecules are lost. I'll put it this way. So as comets pass through the atmosphere of Earth, they transfer some molecules to the Earth's atmosphere. And by the time they, due to a collision with another comet or a larger body, this volatile surface basically disintegrates. And eventually the material gets transferred to, the atmosphere of various planets, notably Earth also. So comets are also sources of, molecules for Earth. Note this point, okay? So this is the first note. And the second point is that comets are sources of interstellar molecules for the Earth. suppose, see, because the comets are lighter than the meteorites, typically they just dissipate away due to the gas molecules getting exhausted. Okay, so but sometimes some very strong comets do fall on Earth also. Okay, but predominantly they die away with the material just getting exhausted. And comets are sources of interstellar molecules for the Earth, just like meteorites. But the mechanism of deposition, or how the molecules are brought to Earth, is different. Okay, so this is the next important point about comets. The next interesting idea about comets is that comets are a source of not just molecules, but intense photochemistry. Remember when we were discussing about interstellar reactions, a lot of these small molecules, the bond could be cleaved by photochemistry, that is by the interaction of some sort of a radiation with the molecule. In comets, that happens a lot. Okay, so comets is a tremendous source of, a comet is a tremendous source of intense photochemistry. For example, while we were discussing about chemical kinetics chemical kinetics in the context of interstellar medium, I was talking to you about the notion of how reaction networks can be developed based on rate constants. Okay, similarly in the chemistry of comets also, you can have reaction networks, right, which arise due to a lot of photochemistry. For example, one plausible example would be one plausible reaction network. This is reaction network. Would be, for example, let's say you start with methane, all in the gas phase, so I'm not writing it down. And what is the origin of this photochemistry? Well, as the comet passes through a lot of these regions, the solar system also contains a lot of radiations, right? So all these radiations cleave many of these bonds. Okay, so let's say, for example, your methane gives rise to methyl radical and a hydrogen radical, and then this methyl radical combines with itself to form, what is this? This is ethane. Okay, right? Yeah, so this molecule is formed. And once this is formed, this further undergoes a dissociation, right? From, again, due to photodissociation, it gives you some ethyl radical. And I'll continue here. This is step 1. This is step 2. This is step 3. These are all the different steps of the reaction network. Or I would say the different step is perhaps not the right phrase. These are all the individual reactions as part of this reaction network. And let's say, once you generate the C2H5 radical, the C2H5 radical reacts with water to generate OH radical, or let's say H radical, and C2H5OH, which is ethanol, which has also been detected in some comets. For example, the Hale-Bopp or something. That's just one name of a comet. All right. So this is the fourth reaction. So such reaction networks are equally plausible in comets, right? Just like in the interstellar medium. So photochemistry is very active, and due to these photochemical reactions, a lot of molecules could be formed in a comet. So cometary chemistry is very rich. In fact, one way to think of is that one way to think of comet is it is a denser molecular cloud denser with respect to what? With respect to the interstellar medium. Okay, right? It's denser with respect to the interstellar medium. So with respect to the interstellar medium, yet which is subject to many more high energy radiations. Higher energy radiations. All right. So please note this. So therefore, the similarity between your interstellar medium and the comets is that both of them can undergo photochemistry, point number one. And akin to the interstellar medium, that is especially the dense molecular clouds, in the comets there is a much denser amount of molecules. Okay, the molecules in the comets are much denser than the interstellar medium. Okay, but alongside, the dense molecular clouds in the interstellar medium are protected and shielded from lots of interstellar radiations which could break apart the molecules. But that is not the case in the comet. So therefore, the chemistry of comets is very rich, and photochemistry plays a major role there. Just note this point. Okay, and because of this rich chemistry involving a lot of networks, right? One specific approximation is crucial. See, to understand the chemistry of comets, which can get very complicated, because see, this was just one network containing four steps. Okay, that is like 4 individual reactions. What if the reaction network is much larger and bigger, right? It will become much more complicated. So to understand the chemistry of comets, oftentimes a prominent approximation is used. Okay, and an approximation is used which is called as a steady state approximation. Now, it is not just to study comets, but also, in the case of interstellar reactions also, because of the similarity here. Okay, so to understand chemistry of comets, note also for what I've written here is also for interstellar reactions. Okay, this is valid even for interstellar reactions. Steady state approximation is used, which simplifies the computation of rate coefficients. And what is the steady state approximation? It is that, let's say, you have all these individual steps as part of the reaction network, right? Now, the CH3 dot, the C2H5 dot, etc. are what are called as intermediates. Okay, right? So, for the steady state approximation, right? For the steady state approximation, the rate of formation of any intermediate is 0. Okay, so this is a very important idea which is used in the chemistry of comets, because this will simplify a lot of things. So how this is done, we shall look in the next class. So what did we see in today's lecture? That is lecture 78. We started off with finishing off the concept of how meteorites aided in the formation of Earth itself. And then we discussed the structure of a comet and how it contains an ion tail and a neutral molecule tail. And followed by that, we understood that photochemistry is an important aspect of the chemistry of comets. And as part of understanding the complicated reaction network present in comets, which is also very similar to what happens in the interstellar medium, although the comet is a much denser environment. In other words, per centimeter cube, it contains more molecules, yet it is subject to intense radiations. Okay, right? So to study the chemical reactions occurring on comet, we typically make an approximation called as a steady state approximation. I just wrote one expression for the steady state approximation, and we shall continue from this in the next lecture. Thanks a lot.